Hey, hi, everybody. We're going to get started here. So thanks for joining the 4th Annual International Day of Women's in Statistics and Data Science. This year's theme is Thriving in Your Environment, and I'm recording the event, so all of the videos will be available on the Caucus for Women in Statistics YouTube channel. And so we'll ask you kindly to post your questions to the speakers in the Q&A chat. And without further ado, on behalf of the International Society for Bayesian Analysis, I'm delighted to open this session, number 206, on advances in high-dimensional modeling, Bayesian modeling. So the first speaker is Gemma Moran, so let's please welcome her. So Gemma, it's all yours.
Hi, everyone. Can you see my slides okay? Great. Thank you so much for Samir for the introduction. It's really exciting to be here and sharing some of our recent work on identifiable nonlinear multi-study factor analysis. So we're in the setting of unsupervised representation learning. We have some high-dimensional data. For example, we might have a matrix of cells versus genes, and we want to understand some latent structure in this high-dimensional data. So our observed data could be gene expression levels, and we want to learn some latent factors that drive variation in this high-dimensional data, which may be associated with some kinds of underlying biological processes. So this is for the single study setting where perhaps we just have one matrix here. We're also interested in this multi-study setting where we now have multiple data sets from different groups. So the motivation for this work comes from data and a study from my collaborator at Rutgers, Anandi Krishnan. She studies platelet biology and has platelet gene expression data from patients with different conditions. And the goal here is to learn some underlying markers of shared versus specific pathobiology, so some shared factors common to these different conditions versus condition-specific latent factors. So to visualize, the idea here is that there is some underlying shared covariance structure represented in this graph here. So here we have these three genes that are driven by some variation in factor Z1, and this is shared across this second study here. But we may have some study-specific factors of variation where we have some correlation structure among our genes that's only present in one study versus another study. So our desiderata for our methods, we want to be flexible in that we want to be able to capture potentially nonlinear associations from this latent space to our observed data space. We also want to retain some measure of interpretability as well, though. And interpretability in this context means what genes are associated with the same latent factor of variation. And that way we can kind of understand, for instance, this first latent factor here, if we know that these three genes are associated with this factor, then we can describe this factor based on these patterns and the selected genes here. We also want identifiability as well. So if there are many possible ways that we can learn this mapping from these Z's to these X's, and we don't have identifiability, then that really hinders our interpretability in this context. And so we want to have some guarantees on when we can actually find some identifiable, or when we have identifiability in this context. So just as an outline for today's talk, I'm going to talk a little bit about the identifiability issues that we see in this setting. I'm going to talk about the single study setting before moving on to this multi-study setting that we're looking at. So in the single study setting, we're going to assume some deep generative model where we have these latent factors Z that are passed through some nonlinear mapping that's unknown to generate our observed data here. So this is a generalization of the linear factor analysis model. Instead of a linear loading matrix, we have this nonlinear mapping here. So we have this pernicious identifiability problem. We can equivalently write this using some theta here, H theta inverse of Z, and then F composed with H. This parameterization can have a very different interpretation, but it's equivalent in terms of the likelihood. So how do we solve these kinds of identifiability problems? So generally, we can place constraints on either the distribution of our latent factors or the functional form of our F. So the idea here is that if F has some kind of, for example, sparse structure, then F composed with H must also have that sparse structure. This limits the possible H's there are, and so the goal is to limit these H's to transformations that we're okay with, such as permutations. So a brief literature review, there have been a large number of works in the past couple of years, especially in machine learning literature, in identifying these kinds of models. So, and they fit into this kind of framework of either placing constraints on the distribution of Z or on the function class of F. I won't spend too much time here, but our work fits into placing constraints on the function class. In particular, we're going to consider sparsity. So just to build some intuition from the linear case, the linear factor analysis model also has identifiability issues. In particular, we can rotate our factors in our loading matrix. This is likelihood equivalent, but our interpretations are completely different in terms of if we're trying to understand this mapping between our latent factors and our observed data. So how can sparsity help? So the idea that we're really going to leverage throughout this talk is the idea of anchor features. And so what is an anchor feature? An anchor feature is a column of the original data. So you can think about this as the expression of gene J for all of our samples that depend only on one dimension of the latent space. So this corresponds to sparsity in the loading matrix. You're only going to have one non-zero value there, and then that will be an anchor feature here. So this idea of anchor features has come up in topic models and in linear factor analysis more recently. And we're going to leverage this idea for the nonlinear case, both for the single study and the multi-study data. So let's talk about the single study data now. So we're going to introduce a sparse deep generative model that has this kind of sparse structure reminiscent of the linear case, where we mask our latent representation Z by some masking W. Now, this means that our Jth feature of the data, so this Jth gene, only depends on a subset of these latent factors. And so we're sort of including this sparse structure that we can leverage in the linear case, but now including this in the deep generative model case. So each of these different features depend on a different subset of our latent factors. And so we can visualize it in this way. We're sort of breaking these connections between the latent factors and the observed data. So we get flexibility from using neural networks. And we also get interpretability from this masking pattern in that we can inspect which features depend on which factors. So the last desiderata we mentioned was identifiability. So generally for identifiability, the classic definition is if two parameters have equal likelihood, these parameters must be equal. We relax this somewhat for the nonlinear setting. We want to identify each dimension of our latent factors up to element-wise transformation and permutation. So here we just want to be able to disentangle the different dimensions. We don't necessarily need the exact mapping in that if I estimate Z1 or Z1 squared, I'm okay as long as I'm not including other dimensions there as well. So we show that we can get identifiability, or these factors are identifiable in this setting under the following assumptions. So we need this anchor feature assumption that I mentioned. So for every factor, there needs to be at least two features that have the same mapping with that factor. Importantly, we don't need to know the anchors in advance, nor how many anchors we have in advance. We also need a condition on the scale of the neural network, which essentially says that the anchor features need to vary more together than the other features. This is satisfied by neural networks with ReLU activations and independent weights. So it's nice that it's satisfied in that setting, but we would like to extend this to trained weights, but this is what we have here. We also need a condition on the factor covariance, where we need sufficient variability within a factor needs to be greater than its covariance with any other factor. So how do we estimate this model? So we have our representation Z. We have some normal prior here. We have our mask matrix here. We want to learn this sparsity pattern. So we're going to be using sparsity inducing priors, specifically the spike and slab lasso by Rutgers and George. So here, a priori, our masking values here, each WJK is drawn from either a spike and encouraged to be small, or a slab and allowed to be large. And this is actually very effective at then learning this latent underlying sparsity pattern. So in terms of fitting the autoencoder, the variational autoencoder, we additionally have this variational approximation on our latent factors, where we assume that there are some Gaussian with some flexible neural network mappings from our observed data here. And we fit this with the usual VAE objective function. Okay, so this is the sparse VAE. Now I'm going to talk about the multi-study setting. So what I've described was for a single data matrix. We're now in this multi-data set setting where we're trying to learn this shared versus study-specific covariance. So there is some related work in the linear setting here I want to point out. So multi-study factor analysis by DeVito et al. More recently, subspace factor analysis and spectral decomposition-assisted multi-study factor analysis. And so we're looking at a nonlinear generalization of this setting. So the idea here is to introduce now a shared masking matrix W. This is going to capture these shared patterns between our studies or between our groups. And then we have these study-specific or group-specific W matrices here that we're going to learn as well. So we can consider a sparse deep generative model again, where we have this kind of masking of our latent factors. And so this is how we can generalize this to the setting with this shared component and this study-specific component here. So the identifiability issue that arises here in particular, in addition to the identifiability issues from the single study case, is that the situation where you put all of the covariance in the study-specific or group-specific structure has the same likelihood as the one where you distinguish the shared versus the study-specific structure. So we want to mitigate this or fix this identifiability issue where you can't separate out this shared versus study-specific information. So in terms of our identifiability result here, so we show that the supports are identifiable under the following assumptions. So these assumptions are inherited from the single study case. We have some additional assumptions that allow us to identify the support of these masking matrices. And then the proof idea is that we can consider each study separately and identify the support. We can then select columns with the same support across all studies to construct the shared matrix. And then because of this anchor assumption as well, the remaining columns are study specific and their intersection of their column space is null. So we're not going to get this mixing here. So this proof is inspired by another paper, Stemmer et al. In 2023 for the linear case, and it's constructed. So in terms of fitting this model, so we have a similar deep generative model as we showed for the single study case. We again are going to use sparsity-inducing priors on our masking matrix and fit these latent factors and our parameters using this variational autoencoder with the EM steps for the masking matrix. So the intuition here and how our model encourages this separation between, or to separate the shared from the study specific instead of estimating them all in the same place, is that the sparsity in the columns forces the model to use the shared entries because it is more sparse if you put signal in those matrices versus the study specific, where you would need more columns to estimate that shared structure. So this sparsity really helps us with this separation and estimation. And so just for a example, here we have synthetic data with 1,000 samples per group, 3 groups, 100 features, and we have some features have a linear mapping and some have a nonlinear mapping with the latent factors. So here are the true W matrices. And so we estimate the true W matrices, separating out that shared versus study specific structure. And I want to point out here as well that we overestimate the number of factors, and we can zero them out to learn the ambient dimensionality of our data. We can also see we recover these linear and nonlinear patterns, both for the shared and then for the study specific, where the pattern is only present in one group. So we can see how the model progresses in terms of learning this sparse structure here. And then finally, we have some preliminary results for this platelet gene expression data that I mentioned. So here we have almost 1,500 patients, 5,000 genes, 6 groups, and we learn these shared and study-specific matrices. To evaluate, we conduct a gene ontology overrepresentation test, which tests if the selected genes are more similar than by chance in terms of gene ontology. And we find that 90% of our columns are enriched for biological processes, so suggesting that it's picking up this real biological signal here. As example, most of these processes, as we might imagine, are associated with the immune system, such as these gene processes that I'm displaying over here. Okay, so with that, thank you very much. So we talked about this identifiable data-driven models by sparse decoding and this in-progress work on multi-study sparsity. So excited to take questions in the chat if there are any, and thanks again for organizing this session.
Thank you so much, Gemma, and right on time. So if you have questions for Gemma, please put them in the Q&A, and we'll move on to our next speaker, Dr. Cecilia Balocchi from the University of Edinburgh. So Cecilia, the floor is all yours.
Hello, thank you so much for the introduction, Samir. Let's see if I can share my slide. And now can you see my slides? Yes, okay, perfect, amazing. Great, so I'm excited to be telling you about this work on improving uncertainty quantification for Bayesian cluster analysis. This work is joint work with a colleague of mine here at the University of Edinburgh, Dr. Sarah Wade. So I'm going to start by giving a brief overview of Bayesian clustering for those who are not familiar with it. And then I'm going to give you some, hopefully some motivation of why we really care about quantifying uncertainty in that context. And give you a background of what we're currently doing already to summarize the posterior over our clustering. And then the main idea of this work is this idea of doing uncertainty quantification via doing an approximation of the posterior distribution. So we're going to talk about that. And then lots of examples and recommendations, some recommendation if I have time for visualizing uncertainty. And then I don't think I'll have time to cover experiments and application, but hopefully this will motivate you to read the paper if you're interested. So clustering is essentially when you have your data points and you want to divide them into groups that are more or less homogeneous. So from a mathematical point of view, we're finding a partition of our data points. Now, there's approaches that are algorithmic and they usually minimize a specific loss, but then they're going to lack uncertainty. So instead, the Bayesian approach gives us a framework to characterize the uncertainty, and it does this by combining a prior distribution over the partitions, the clusterings, together with a model or a likelihood that gives us a way to assess similarity within the points in a given cluster or group. By combining prior and model, we get a posterior over the clustering over the partitions, which you can also think of as a weighted ensemble of clustering solutions. So we're going to be focusing on model-based clustering, which is essentially relying on mixtures. For mixtures, you need to specify a parametric kernel density, which is quite important in the model. But also something that's important related to this is that essentially this induces a random partition where each of the clusters, say Cj, contains the indices of the data points that belong to the same cluster. And the interpretation associated to this is that the points associated with that cluster are generated from the same mixture component. And this is how we think that the points are within a cluster are all homogeneous. So there's various things that we need to consider, and one of these is choosing the number of clusters. There's various approaches. Maybe one that you're familiar with is the finite mixture model, when you're essentially fixing the number of clusters to a finite number, and then you run it for different values, and then you choose the best one based on base factor and information criteria. However, in this work, we're going to focus on the last three of these possible options because they induce a prior on the whole space of partition without restricting to a specific number of clusters. And in practice, when they're going to infer the partition, they're going to automatically infer the number of clusters and account for the uncertainty in the number of clusters in this way. So these are, for example, putting a prior on the number of clusters. That's mixtures of finite mixtures. You can set K to be very large and have some of the clusters to be empty. This is what is called overfitted mixtures. Or you can have infinite mixtures where K is sort of to go to infinity, which is the sort of maybe more traditional Bayesian non-parametric approach. So now, how do we fit a Bayesian clustering model? The thing is that computing the posterior exactly is very complicated because we are working on the partition space. We're interested in the posterior over the space of partition, and this space of partition is discrete, it's unordered, and it has massive dimension. So essentially, the total number of possible partitions for clustering 10 data points is more than 100,000. If you have 20 data points, the number of partition is, I think if I counted the number of digits correctly, it's 51 times 10 to the greater than 51 times 10 to the 12. So it's a very, very large number. We clearly cannot deal with this, and so people use MCMC. They produce tens of thousands of clustering solutions that represent their posterior draws, and then they need to summarize these posterior draws, and some of the problems are that sometimes there's label switching, sometimes the number of clusters changes, so there's things to keep in mind when we do this. So to give you another visual representation of this space of partition, so before I said the space of partition is unordered, we actually do have a partial order, and it's what's represented in this diagram here on the left-hand side. So this picture is called a Hasse diagram, and essentially it's what we get when we have a lattice. So the partial order that we have in this space is defined by the relationship of set containment. And so for the partitions of 4 data points only, this is what the space looks like. So imagine essentially a very large discrete space where you can draw some relationship between different partitions based on whether they're close to each other given this partial relationship. So as you can imagine, we cannot use the usual tools to summarize the posterior. So you can't just create a credible interval in this context. You clearly cannot use mean and standard deviation to do that. So I hope this kind of gives you an idea of why we need to think carefully of how we understand and explain the uncertainty in our posterior, which is over this very complex space. Okay. So what is currently available? Now, first of all, whenever you've done MCMC, you first want to find a point estimate for your partition. And now possible ways to do this are, for example, you want to find the mode of your distribution. This is called the maximum a posteriori partition. Or there are some ad hoc approaches. So sometimes people use the posterior similarity matrix, which is an n by n matrix of posterior probabilities of co-clustering, so pairwise probabilities. And they use these as an input to, say, hierarchical clustering or something else to find a partition. Or you could go with what Wade and Garamani suggested in 2018, and estimate the full clustering solution using a decision theoretic framework. Now, whenever we're using decision theory, essentially, we need to choose a loss, and then in the Bayesian context, we know that we can find the estimator that minimizes the posterior expected loss. Now, which loss do we use? So one could use a 0-1 loss, for example. This is very generic, it's often used, but the problem is that well, not a problem, but it has some disadvantages, but also essentially it's going to lead back to the mode, so the maximum posteriori partition. There's various reasons why we might want to use some partition-specific losses, and this could be distances on the space of partitions. Two of those, the ones that I'm listed here, are one, the binder distance and the variation of information distance. And because of the various properties of these distances, we're going to focus on the variation of information loss. And if you're more interested in this, I can answer some questions later, or you can have a look at the paper by Wade and Garamani, who kind of explain why the variation of information tends to have better properties. So now we know that our estimator is going to be the one that minimizes the posterior expected loss. So essentially is minimizing the posterior expected VI, so that's why we call it the mini VI. I'm going to use this sort of name to refer to this estimator. All right, that's it for kind of point estimates. What about uncertainty quantification? Now, right now, what people currently use, they often use this posterior similarity matrix, and they construct credible balls. Now, this again was recommended by Wade and Garamani, and is essentially an extension of credible intervals in the context of the space of partitions. The problem with this is that there's some computational difficulties into constructing this, and so sometimes they're not so easy to construct. So we want to add one more tool to this list, which is the idea of using multiple point estimates to summarize our posterior. And I'm going to give you a motivation for this. And this example is a very simple toy example where you have a mixture of two Gaussian distributions. They have very close means. This was motivated by a work of Rajkovsky that proved that even asymptotically, the maximum a posteriori partition is going to be the partition with one cluster, even in this data generating process, even though it's then generated from two mixtures of Gaussians. And empirically, we do see that the mini-VI estimator is the partition with one cluster as well. However, when you go and look at the posterior similarity matrix, you see something like this. Now, the two orange blocks that you see essentially tells us that there's these two blocks of points that are often co-clustered together and not co-clustered with the other set of points as often. So this is essentially saying that a lot of the posterior samples are actually splitting the data in two clusters. So this is kind of frustrating because one estimator is telling you something, but then you don't really have the tools to summarize your posterior to explain what's going on in the posterior similarity matrix. So this is where our contribution comes in, and the idea of summarizing the posterior with several estimators is to take your posterior distribution over the space of partition, so P of gamma given your data, and approximate it with another distribution that's discrete, but it's supported on a much smaller number of partitions. So they're both discrete distribution because they're supported on the space of partitions, but now we're gonna choose these distributions so that the number of support points is much smaller. And we call these support points the particles, and you're gonna see why in a moment. So we're gonna do this approximation in a Wasserstein distance sense. And whenever we work with the Wasserstein distance, we need to also choose a distance on the actual space we're working on. So here we're working on the space of partition, so we're gonna use a distance on the space of partition. And we're gonna focus on the VI distance for the reason I mentioned before, but this could be extended to other distances as well. So if you're not familiar with the Wasserstein distance, this essentially is defined with a minimization problem over the set of couplings between the two distributions. And I don't want to go too much into the details of this, but essentially we use this definition to then find the solution to our problem. So the method that we propose is called Wasabi, so Wasserstein approximation for Bayesian clustering. And what happens for the special case if we were to approximate our posterior with just one estimator? So this is kind of maybe a more trivial case, but it's still interesting to see what happens. And it turns out that we do recover the original estimator that we started from, the mini VI estimator, which kind of makes sense. It's kind of closing the loop that if we're not using multiple estimators, we're just going up to approximate with one, we find the estimator that the decision in theory approach tells us we should use. So that's great. Now, what about the kind of case in which we're using a greater number of particles? So essentially, we can write our objective function, and essentially we get it written down as a sum over the partition, over the whole space of partition, but this is broken down over these regions, these neighborhoods or region of attractions. And the way they're defined is essentially they're looking at the partitions that are closer to one specific particle compared to any of the other ones. So essentially we're partitioning the space of partitions into these regions of attractions. And then we're also able to rewrite it again, our objective function, as a sum over the particles of their expected VI restricted over these regions of attractions. So if you're not familiar with this, or you're not following, that's fine. We have very limited time. But let me tell you, this is essentially the same objective function that we have when we look at K-medioids, which is a sort of an extension of a K-means approach. And I'm going to use this to give you an intuition of how the algorithm works and how we find our solution to this optimization problem. So we also can show that the optimal weights associated to these approximations essentially are the posterior mass associated to each of these regions of attractions. So in practice, we said that though we don't really have access to that posterior distribution, we only have access to the MCMC samples that we obtain from our posterior inference. And so instead of directly approximating the full posterior, we approximate our empirical estimation, our empirical distribution of the posterior distribution. So essentially we use our MCMC samples to approximate the posterior, and then we do an approximation with Q of our empirical posterior distribution. So everything can be redefined in this context, and so now the regions of attraction, they're defined not on the whole space of partitions, but just on our MCMC samples. So we're going to be partitioning our MCMC samples into these regions of attractions. Okay, so this illustration is sort of to give you an idea. I showed you before that Hasse diagram. Now imagine that this grows for a much larger number of points. So you now have a discrete space which is kind of difficult to describe. So this illustration is sort of not supposed to be realistic, but essentially you have lots of points that are connected based on the partial order relationship that we have on that space. And imagine that now we're coloring the points based on their posterior distribution. So in this case, I'm representing a posterior distribution that is bimodal over the space of partitions. So there's two regions that have a sort of high posterior mass. Okay, now, assuming we've done MCMC, our MCMC has mixed and has explored the space, and these are our MCMC sample. The algorithm works by alternating two steps. First, it's going to condition on an estimate of the particles, and it's going to define what the regions of attractions are. And then conditioning on the regions of attraction is going to update the value of the particles by finding the mean EVI estimator for that region of attraction. So that's kind of the two alternative steps that we take to actually solve this problem. And then ideally, if everything works, then we find the particles that represent the two mean EVI estimator for these two regions of the space. So the algorithm is very similar to chimeridoids, so we need to think carefully about initialization. We're going to be relying on algorithms that already work well for finding the mean EVI in each of the region, and we use strategies like mini-batch. We also need to choose the number of particles. So, and for this, we recommend doing the method for values of the number of particles, and then look at the elbow method, use the elbow method and look at the elbow plot. So essentially, for that bimodal example that I showed you before, it looks like the number of recommended particles to use is 2. We can start by visualizing their weight and the number of clusters. So here, the first particle has 70% of the weight, and it's the partition with one cluster only, so everyone together. And then the second particle has 30% of the weight, but it's actually a partition with 2 clusters now. And we can look, say, at the range of the data in each of these 2 clusters, and we can see that actually splitting the data in half, so or approximately in half, so the sort of left half and the right-hand half. What about another example? And maybe this is mixtures of 4 two-dimensional Gaussian distributions. If we look at the posterior similarity matrix, we see that there's 3 or 4 components maybe. And if we run a rainbow plot, we choose maybe, say, 3 particles here. And we find that in this case, we get 3 partitions, 1 with 1 cluster and 2 with 3 clusters. And we can see, for example, the scatter plot with each point colored by the cluster assignment, and visualize how different they are. And what is interesting here is that these partitions, they're very different. They're not something that you would be able to get if you would be doing something like hierarchical clustering. Now, I think I am mostly running out of time, so I will wrap up. These are some of the visualization. We have some tools to also sort of understand a bit more in the uncertainty in the cluster allocation of individual data points, but I'll send you to the paper and I'll wrap up. So this is sort of what I've described today, sort of next steps. In this is essentially extend this to other losses and other settings, and we're almost at the closing point for integrating that in our R package. And also something we're thinking about is, can we use this to understand uncertainty in the posterior for other non-standard parameter space in different settings. So thank a lot for your attention, and yeah, I'm happy to take any questions later.
Right. Well, thank you so much, Cecilia. There is a question in the Q&A, and I can read it out for you. The question is, why do you choose to use the Wasserstein distance here? Is there any useful property that sort of motivates this choice?
Yeah, that's an interesting question. Actually, in one of our previous work, we did a similar approximation where we were using the Kullback-Leibler divergence, and we found out that in that case, we were targeting the L most, or like partition with the highest posterior, and that was actually not summarizing the posterior in the sense that we mean here. And it turns out that just by the way that the Wasserstein distance work, we get a much more, we get this interpretation that the approximation that we get in this sense will target the different modes rather than, say, something that we would get with callback library that instead targeted, sorry, maybe I can show you this picture. With the callback library, we would probably target very similar partitions that all have the largest posterior. Well, in this case, we're able to target particles that are different from each other. So this allows us to really understand whether there is multimodality in our posterior, and so look at a different side of this posterior uncertainty quantification question. Hopefully this answers the question.
Great, thank you so much. Okay, so we were planning to have a talk by Elizabeth Bersson from MIT, but I somehow don't see Betsy in the list of attendees. So if you are here and maybe registered under a different name, can you just raise your hand? And if not, we have plenty of time for questions of both of our speakers. So failing to see Betsy in the attendee list, I have a couple of questions for both speakers. So maybe Gemma, can you comment a little bit more about the scalability? Right, you're putting these spike and slab priors on those sort of masking weights, and that seems like they could be quite a lot. So if you wanted to do, and I sort of missed, were you doing kind of a variational thing or finding a mode, or were you doing full MCMC? Like how feasible would it be to explore the posterior here?
Yeah, great question. So we're doing map estimation for the sparsity parameter. So we're not doing MCMC, so we're not getting this uncertainty in that sense. It is rather scalable in that, so I am fitting models with, 5,000 samples and, 5,000 genes. And well, yeah, I guess on a laptop, that might be an hour. On GPUs, that could be 15 minutes because we're using neural networks here. But yeah, it's fairly scalable. I think that another nice aspect is you can really like over initialize the number of factors and then sparsify and actually